Population modelling of a selectively bred species. The Leslie matrix method. The Leslie matrix method is a population modelling method which uses the age distribution to forecast future behaviour of a population. It uses survival and fecundity rates to form a Leslie matrix which can be multiplied by an initial population distribution to predict the population of the next time period. The fecundity rate is the number of offspring born per year as a percentage of the total number of mature females. The survival rate from it is the probability of an individual continuing from one age class to the next.
The single-sex Leslie matrix model only considers the female population. It is used by dividing the female population into age classes. The age classes must be of equal duration, and the unit of time within the model is the interval between these age classes. The population distribution forecast is calculated by multiplying the Leslie matrix by the vector containing the initial values of the population distribution. The two-sex Leslie matrix model. As with the single-sex method, the population distribution forecast is calculated by multiplying the Leslie matrix by the vector containing the initial values of the population distribution. The population distribution forecast is calculated by multiplying the two-sex Leslie matrix by the vector containing the initial values of the population distribution. Exploitation of the two-sex Leslie matrix method. The two-sex Leslie matrix model works the same way as the single-sex Leslie matrix model for forecasting exploited population behaviour. The Leslie matrix has to be adapted for both males and females. The extermination matrix is calculated in the same way, a diagonal matrix with the elements of the leading diagonal being the extermination rates of the female and male age classes. Subtracting the extermination matrix from the identity matrix gives the hunting matrix. Multiplying the hunting matrix by the two-sex Leslie matrix forms the transition matrix T, which can then be multiplied by the initial population vector to forecast the future population behaviour of the exploited data.
Horse racing. Horse racing is an ever-growing industry in Great Britain and attracts over 5 million racegoers, attending over 1,000 racing fixtures and more than 92,000 horses running in over 9,000 races every year. On average, more than 14,000 racehorses are in training each month, with the goal of winning prize money, which totals greater than £90 million per year. These fixtures are taken from the British Horse Racing Board's Annual Report 2010. How does this affect the population of the racehorse? Initial age structure of a female racehorse is used alongside the Leslie matrix to forecast future population. The Leslie matrix is formed using the survival and fecundity rates. As female racehorses are not mature until they are 4 years old, the fecundity rates for 2- and 3-year-olds will be 0.
The Leslie matrix for the female population of racehorses is as follows. The population can now be forecast using the formula on the screen.
These are forecasted population distributions across the age classes over the next 15 years. The population appears to be increasing over this time. By looking at this graph, it can be seen that the population of female racehorses is increasing. The increase looks to be demonstrating an exponential growth. Using the power method, it has been found that the dominant eigenvalue of the matrix L is 1.2994 and the corresponding eigenvector is 1, 0.5156, 0.3969, 0.3024, 0.1536, 0.4465. This means that the population of female racehorses is growing eventually at a rate of 30% per year, so the population of the female racehorse in Great Britain will grow and eventually reach a steady state of growth. By dividing through this dominant eigenvector by the sum of the components within the eigenvector, the stable age distribution can be found. This shows that once the behaviour of the population growth reaches a steady state, approximately 35% of the population will be 2-year-olds, 18% will be 3-year-olds, 14% will be 4-year-olds, 10% will be 5-year-olds, 5% will be 6-year-olds, and 15% will be 7 years and over.
Population distribution of horses in 2010 is shown on screen.
The survival and fecundity rates of male and female racehorses can be used to produce a two-sex Leslie matrix. This matrix can now be multiplied by the initial population distribution. This graph shows that the population of racehorses for both males and females is increasing. This increase looks to be demonstrating an exponential growth for both sexes across all age classes, although some age classes are increasing more rapidly than others. It has been shown that the population of racehorses is increasing at an apparently exponential rate. To find the steady state growth of the distribution of the population across the age classes, the power method has been used, and it has been found that the dominant eigenvalue of the matrix is 1.2993. This means that the entire population of racehorses is increasing eventually at a rate of 30% per year, so the entire population of racehorses in Great Britain will grow continuously and eventually reach this steady state of growth. This confirms the exponential growth that can be seen in the graph. By dividing through the eigenvector, which corresponds to the dominant eigenvalue, by the sum of the components in the eigenvector, the stable state of age distribution is shown. To explore the effects that deaths on the racetrack have on the growing population of both male and female racehorses, an extermination matrix needs to be formed. For this, extermination rates are used. These were calculated by taking the number of deaths in 2010 as a percentage of the total population for that age class. From the extermination matrix, the track death matrix is formed by subtracting the extermination matrix from the identity matrix. Multiplying the track death matrix by the two-sex Leslie matrix produces the transition matrix. From this graph, a minimal period of cyclic behaviour within the first 10 years within most age classes occurs. However, after that, population begins to grow, possibly exponentially. This can be examined further using the power method. It was found that the dominant eigenvalue for the exploited transition matrix was 1.1747. This means that even with the horses dying on the racetrack, the population of racehorses is still increasing at a rate of 17% per year. How would altering the minimum age for horses to race affect the population growth? By removing the data for those horses who are less than or equal to 3 years old, will the population still grow? For this, form a new Leslie matrix model, applying the power method to give a dominant eigenvalue of 1.8876. This means that when the racehorses are restricted to being aged 4 years and over, the population, when a steady state of growth is reached, is increasing by 89% per year. What effect would raising the minimum age for racehorses have on the deaths of racehorses on the track? By altering the extermination matrix so it does not include horses younger than 4, it forms the following transition matrix. Applying the power method to this produces the dominant eigenvalue 1.7223. This shows that when the minimum age for racehorses is altered to being greater than or equal to 4 years old and the deaths of the racetrack are also considered, the population of racehorses is increasing at a rate of 72% per year. The steady state age distribution for this population is shown. So far, we have only considered the population of mares and stallions in the data set, as they are the only ones with the ability to reproduce. There is a large portion of the racehorse population who are geldings or castrated males. The fecundity rates of both males and females would remain the same if the number of geldings was included, as they produce no offspring. They will, however, contribute to the survival rates for males. This forms a new Leslie matrix model. Using the power method on this Leslie matrix model, we can find the dominant eigenvalue is 1.2993. This shows that once the population growth reaches steady state, the population will be increasing at a rate of 30% per year. The steady state population distribution is shown. The analysis of the female racehorses showed that once population growth reaches a steady state, the population will be increasing at a rate of 30% per year, with the largest percentage of the population being 2-year-old mares, with 36% of the population being in this category. The population growth for the male and female data reaches steady state at 30% per year. This is the same as the population growth for the female population on its own. The population split relatively evenly, with 44% of the population being female and 56% 6% of the population being male. Both male and female age distributions are similar across the age classes, with both males and females having the highest percentage of populations being 2-year-olds and their lowest percentage of populations being 6-year-olds. Deaths of horses on the racetrack is a very controversial subject, with many people being against horse racing and classifying it as cruel. However, according to the rate of steady growth for the exploited dataset, which is the data which considers the number of deaths on the racetrack, even with the number of deaths continuing at the rate in which it is growing, the total population of both male and female racehorses will still be growing at a rate of 17% per year. This is less than the rate of growth for the unexploited dataset. However, it shows that the deaths of horses on racetrack will not lead to the extinction of racehorses. By enforcing a minimum age for racehorses to be 4 years old, it is found that the rate of growth once steady state behaviour has been reached will be 89% per year. This is larger percentage growth than the one found when horses aged 2 and 3 years old were also allowed to race. It was found that the rate of growth for the population when the minimum racing age for horses is 4 years old and the racetrack death was considered to form the exploited dataset. It was found that the rate of growth was 72%, which is only slightly lower than the
unexploited data.
It can be deduced that enforcing a minimum age of 4 years old has reduced the effect of the death on the racetrack to the population growth, as before this was enforced, the racetrack deaths changed the rate of growth from 30% to 17% per year. With this enforced, racetrack deaths brought the population growth from 89% per year to 72% per year, which is only a 20% decrease in population growth. Including geldings or castrated males in the dataset had little effect on the population growth and the steady state distribution. The growth rate at steady state behaviour was found to be 30%, as it was said to be when castrated males were not included. The percentage population distribution across the age classes at steady state was also very similar to that which was found for the populations which didn't include castrated males. It is suspected that this is due to the geldings' lack of ability to reproduce, causing them to have little effect on future forecasted populations.